Hello and welcome to Cup of Cosmology, the place for all your questions about the universe. My name is Diana Hooper and I'm a postdoctoral researcher currently at the Helsinki Institute of Physics over in Finland. I'm a cosmologist, so that means that I study the universe, the contents of the universe, how everything evolves, how everything interacts, basically everything happening inside the universe. It's really fun. I love studying the universe, I love being a cosmologist, and I really like chatting to everybody about all of the cool things happening inside the universe and about science in general and about everything related to basically my scientific life. And yeah, I love coming here and doing live streams where I chat to everyone and answer anybody's questions. Now, I hope the YouTube connection worked. If anyone is watching from YouTube, please do let me know that it is coming through, because it always takes a minute to synchronize up with YouTube. So please do let me know if the YouTube stream is working. In fact, I will just check on the YouTube stream myself while everybody comes in. So yeah, as I said, I'm a theoretical physicist, currently always studying cosmology at the I'm a theoretical physicist specializing in cosmology, and currently I'm based at the Helsinki Institute of Physics. YouTube is up. Thank you, Paul. Thank you, James, and hello to both of you. Thank you for confirming that YouTube is indeed working. You saw there that I'm not good at multitasking. I tried to open YouTube to confirm that, and I lost track of my sentences. This is why I don't try to multitask. So great to see everyone. Thank you for joining. Thank you, as always. Some of you have been here from following me since the beginning now, and it's always great to see you coming back. So yeah, I'm a theoretical physicist. I specialize in cosmology. Hey, David, great to see you as well. And I love talking about the universe and all of the cool things happening inside the universe. And Cup of Cosmology, what we're doing here today, this live stream, is a place for everyone to ask all of your questions about space, about science, about cosmology, about academia. I would not recommend asking me about academia this week because it has been a week. Whew. Last week's stream was about all of the good things about academia, and I'm definitely not going to rant, but maybe don't ask me about academia this week. Hello, other David. Great to see both Davids in here, as always. Very, very nice to see you all. So, as always, if people have any questions about the universe, about cosmology, about anything you want, feel free to ask, and I will do my best to answer everybody's questions. In the meantime, I do actually have a topic prepared today, or at least something I want to talk about, as you might see from the title of the stream. Now, there is a reason I'm doing this specific topic this week. So there are two reasons, actually. The first one is I love the CMB. So anyone who's joined my stream at any point will have heard me talk about the CMB, the cosmic microwave background radiation. It is it is without doubt my favorite thing in the universe. It is an amazing thing that we have access to that gives us a huge amount of information about the universe. Now, hey Sabora, nice to see you as well. Hello and welcome if you're new here. So on the one hand, I love the CMB, and I have not done a specific stream dedicated to the CMB in about a year. But the real reason I'm doing this stream this week is that somebody said to me at some point during the week that the CMB is boring and that there is nothing left to be done with the CMB. Now, of course, this is blasphemous, and this cannot be allowed to stand. So today, the purpose of the stream, apart from to remind everybody of just how awesome the CMB is, I hope today to show you that there is still a lot more we can do with the CMB. Did we find a secret message hidden in the CMB this week? We did not, unfortunately. No, not to my knowledge at least. And if there's a secret message in the CMB, I probably won't be allowed to tell you, but no. To the best of our knowledge, there is no secret message within the CMB. But the CMB still does have a lot of secrets that we need to uncover. So great segue there. So there is Hey Kumar, great to see you as well. Hello. Please like the broadcast. Yes, thank you for the reminder, David. If you like what I'm doing, please click the like button, leave a comment, subscribe to the YouTube channel if you haven't already. This is how we build up the network. And after HAPS closed recently, I do have to rebuild my audience. I know a lot of people didn't make the jump over between HAPS and YouTube. So please do help with the engagement. Click the like button. It does help with the YouTube algorithm, and then it promotes the stream, and then I get more people joining. So please do all the things that you usually do on YouTube. The buttons, you all know how the buttons work, I hope. If not, just find a big thumbs up and click that one. So yeah, CMB is one of my favorite topics in the universe, and someone disrespected the CMB this week, and that cannot be allowed to stand. Hey Rohit, great to see you as well. So this motivated me to do another stream entirely about the CMB, just to remind everybody that it is a very cool thing, and that despite how much it has told us, there is still a lot more to be done with the CMB. So we have a lot to talk about today. And as my regulars know, when I talk about the CMB, I talk quickly and I talk for a long time. So we might be here for a while today. But let's jump straight into it. What is the CMB? The cosmic microwave background radiation. Now, the cosmic microwave background radiation is the oldest light we can see in any direction we look in the night sky. And it is really the afterglow of the Big Bang itself. It is the background light that decoupled, that broke away from everything else in the very, very early universe. So in the very early universe, we had four main components. We had dark matter that was just doing its thing, not really interacting with anything, just sat there, clustering together, attracting everything gravitationally. And then we had the three main components that we're interested in. We had protons, we had electrons, and we had photons, which were particles of light. Now, in the early universe, when everything was very, very hot, all of these things could constantly bump into each other. So the photons would bump into the electrons would bump into the protons. They were all constantly talking to each other. This also meant that the universe was very dark because the photons, which are the particles of light, could not travel far because they would start traveling and they would bump into something. Imagine if you're at a crowded party and you're trying to cross a room, and every time you try to walk through the room, someone comes and talks to you. You can't cross the room. So this is the problem that photons had in the early universe. They were constantly bumping into the protons and the electrons. If I am talking too quickly, please do let me know in the comments. I know when we get started on the CMB, I do speak quickly. Anyone or institution credited with finding or confirming CMB, or was it just collaborative over time? Great question. That is a very nice question, James, and let me get to that in a few minutes because we'll come back to that question. So we have these three components in the universe. Dark matter is doing its own thing. We have photons, particles of light, we have electrons, and we have protons, and these are constantly bumping into each other. Now, as the universe gradually cooled down, the electrons and the protons could combine together to form the first hydrogen atoms in the universe. Once this happened, the photons, the particles of light, could no longer bump into the protons and electrons. They basically became like a third wheel. The protons and the electrons got together. The universe didn't believe in polygamy at that point, so the photons couldn't really join the conversation, and so they broke away. Once the photons broke away, they started traveling throughout the universe, and they have been traveling freely ever since. Today, these photons make up the cosmic microwave background radiation, this background light that we can see in every direction we look. Now, the cool thing, I mentioned before that we had dark matter in the early universe. Now, dark matter was pulling things together. Where there was a lot of dark matter, there were a lot of protons. There were also a lot of electrons, because this is how gravity pulls things together. Which means there were regions in the early universe where you had more density and regions where you had less density. Now, when the protons and the electrons combined together and these photons broke away, they broke away from underdense and overdense regions. Now, the regions that were overdense, the photon already lost energy escaping the gravitational potential before traveling towards us, while the ones that were on underdense regions didn't have so much effort to do, so they lost less energy. Over thousands and thousands of years, we're talking about events that happened 13.8 billion years ago in the very, very early universe, 13.5 billion years ago. Now, these photons have gradually been redshifted. This means they've gradually stretched. Their wavelength is pushed more and more towards the red end of the electromagnetic spectrum. This means that everything has gradually been getting cooler and less energetic. Now, when we look at these photons today, we see that they have almost the same temperature at about 2.73 degrees Kelvin, which is minus 270 degrees Celsius, which is minus 440 degrees Fahrenheit. So they're very, very cold. And all of these photons have approximately the same temperature, with tiny, 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 tiny temperature differences that come from these overdense and underdense regions. The ones that had to climb out of these potential wells coming from the overdense regions have lost a bit more energy, and so today they are a bit colder, whereas the other ones are still slightly hotter. So when we look at the night sky around us, in the background, behind the stars, behind everything else, there is this afterglow. There is the cosmic microwave background radiation. And if we can measure the cosmic microwave background radiation, we can understand what the universe looked like 380,000 years after the Big Bang, which is pretty impressive. And this is not just a hypothetical. This is something we have done several times by now. So, bit of history of the CMB. The CMB, cosmic microwave background radiation, was predicted in, I don't know why I try to do history and then immediately forget my dates. In the middle 20th century, the CMB was predicted as a clear thing that if our understanding of the universe is correct, the CMB should exist. Then in 1968, Penzias and Wilson were doing an experiment where they had a telescope and they were just trying to look at some stuff in the universe. And they kept getting this background signal that they could not get rid of in their telescopes. There was something there. And they didn't know what it was, and they went out and cleaned the telescope. There's a funny story that they thought there were pigeon droppings on the telescope. They cleaned it, they still got this background signal. And then there was actually, I believe it was at a bar one day, they were discussing this annoying background signal, and a theoretical physicist overheard them and came over and was like, wait, do you guys said you're detecting something? Because what you're measuring might actually be the CMB. And they confirmed that indeed what Penzias and Wilson were accidentally measuring was the cosmic microwave background radiation. And Penzias and Wilson were awarded the Nobel Prize a few years later for the accidental discovery of the CMB. So it's something that was theoretically predicted, and it was then observed. Now, when it was predicted to have this average uniform temperature, to be a perfect black body, perfect distribution of temperatures. However, several years later, it was predicted that not only should we have this background light, which Penzias and Wilson measured, but there should be these tiny, tiny, tiny deviations in temperature coming from the overdensities and underdensities in the early universe. So, the hot Big Bang cosmology predicts there should be this background light. This background light was found by Penzias and Wilson, and it was later further predicted that in order to understand, based on our understanding of the universe, this background light should have these tiny, tiny, tiny temperature differences. So the next challenge was to measure these tiny, tiny temperature differences. And now let me go back to the three questions here. So anyone or institution credited with finding or confirming the CMB, I think I've addressed that. That would be Penzias and Wilson. But we will come back to the actual observations of these temperature differences. Does the redshift due to time add inexactness or interpretation to the CMB, or is it in effect completely known to the extent that it can be 100% accounted for? This is a great question. Now, the cool thing here is that these photons are coming from every direction, and they should all experience approximately the same amount of redshift. Now, there are some differences. One big difference, for an example, can happen. Imagine if a photon falls into a potential or a gravitational well, which is just a region where you might have a galaxy. So imagine you have this photon coming from the CMB, it finds a galaxy, it falls into the gravitational potential, and then it comes out. This falling into the gravitational potential is because space-time is bent because of the presence of this galaxy. Now, usually the photon is going to gain energy when it falls in and lose energy when it climbs out. And it will gain and lose the same amount of energy, so the net effect cancels out. However, while this photon is traveling, what can happen is that the universe expands, which we know is the case. So when it falls into the potential, it gains a certain amount of energy, and then when it comes out, the universe has been stretched, this potential is no longer the same size, and so it doesn't give back the same amount of energy. And this is something we can account for. So when we look at the CMB, the cosmic microwave background radiation, not only can we understand the early universe, but we can get a snapshot of what might have happened while it was traveling towards us. So we can very much account for the redshift. It is an effect that is well studied. Always good to have a theoretical physicist along with you at the bar. Definitely, definitely. And they are very good at opening up tables. You know, you have a bunch of theoretical physicists together, they'll start talking about random topics, and suddenly people move away. It does actually work sometimes. You go somewhere and start talking about black holes or alternative universes, and people give you space. My tea is still too hot. It's good to note before I burn myself. Okay, so brief recap here. We have the photons in the early universe that break away from the protons and the electrons, and they start traveling throughout the universe. This happened 380,000 years after the Big Bang, or approximately 13.5 billion years ago. This was a prediction made by hot Big Bang cosmology based on our understanding of the universe. This was then observed accidentally by Penzias and Wilson. A few years later, it was actually predicted that there should be tiny, tiny, tiny temperature differences. These photons that we see in the night sky should not all have the same temperature. There should be these tiny differences. So now we had to measure these tiny differences. Make sure there are plenty of napkins too. Yeah, we always need napkins because then we can do a back of the napkin calculation. I know physicists love doing random equations, some of them. So honestly, I like maths. I like equations sometimes, but also, but doing back of the envelope calculations or back of the napkin calculations is always funny. It's like, oh, I need to. It's playing into the idea of, oh, I need something to write on, and there's nothing at hand. Let me just grab a napkin. But honestly, I always have pen and paper around with me, so I never need to reach for napkins to do back of the napkin calculation. Anyway, went on a tangent there. So the mission now was to the mission, whether you choose to accept it or not. Today we might be going on a few tangents and rambling slightly. This is because I have had 3 cups of wine today, and I am not a wine drinker. I'm not an alcohol drinker at all, and I have had a bit too much wine and way too many cookies that I baked yesterday because I was comfort baking, stress baking. So with the combination of the sugar rush and a bit of wine, today we are going to go off on multiple tangents. But let's just go with it. The CMB will keep me on topic, I hope. So the mission was make paper great again. Let's not go there. Let's not go there. Back on topic. CMB. So the mission now is to try to measure these tiny, tiny, tiny temperature differences in the CMB, in the cosmic microwave background radiation. And we have now done this with 3 different missions to incredible precision. And for this, I have to bring something up on screen. You should have warned us so we could have done the same prep. Yeah, I should have warned you. Someday we will actually do like a full-on drunk stream. Maybe once I have tenure track position, because I know that will involve copious amounts of ranting. Okay, so there is now an image on the screen, which is one that I've not shown people before. And you might notice that this looks very much like I'm sharing slides from a presentation. And this is exactly what I am doing, because I haven't yet figured out how to share images in Restream, which is odd, but I can upload PowerPoint presentations or PDF presentations. And because last year I gave a talk about the CMB, I was asked to give a talk about the CMB, which is amazing. I've just pulled up my slides that I made for that talk because I have all of the images I need in my slides. So you'll notice the affiliation in the bottom left is wrong. This is my old affiliation. I am currently at the University of Helsinki. And in the bottom right, you'll notice that this was for the conference Cosmology from Home 2021. This talk is on YouTube and it is publicly available, but it is aimed at other scientists. So the language is a bit more technical than what I do in my streams. From right to left, 0 cups of wine, 2 cups of wine, 4 cups of wine. Yes. So what you can see up here in this amazing image is a composite of all of the measurements we've been able to do, or the best measurements we have from each mission, trying to measure these tiny, tiny, tiny temperature differences in the CMB. And the first one you see here on the left is the COBE mission, which was launched in the early 1990s. This was the first mission that was able to find, without a shadow of a doubt, that we had these tiny, tiny, tiny temperature differences in the CMB. And you can see it here with these blue and pink splodges. So the precision is not perfect, it's not great, but it was enough to confirm that these temperature differences are there, that our understanding of the universe was correct. In the early 2000s, there was another mission, which was a ground-based mission known as COBE. Known as Boomerang, and Boomerang was able to measure the same as COBE. So then we had 2 missions that measured the same thing with similar precision. But this was not enough. We needed more precision, we needed more details. And then in the early 2000s, we got the WMAP mission. WMAP was launched in 2003. It ran for 9 years and it released a lot of maps of these temperature differences. So what we're measuring here really is the CMB temperature. So we look at the photons coming from every direction in the night sky, we measure their temperature, and we plot the tiny, tiny, tiny temperature differences that we can see. So first we had COBE, then we had WMAP, which you can see here in the middle, which you can see really starts to pick out these hot spots and cold spots. And it really started to have good precision, but still not quite as good enough as we wanted. And then in 2009, the Planck mission launched. So I should just say that these were NASA missions and ESA missions, a combination of both. Then in 2009, the Planck mission launched. And Planck was able to give us the map that you can see here on the right-hand side, which is the one you've all seen me use multiple times. This is incredible precision. The Planck satellite was able to measure these tiny, tiny, tiny temperature differences with percent level precision. And I say these temperature differences are tiny, and what I mean here is that it's 1 part in 100,000. 1 part in 100,000. So we're looking at really, really, really tiny temperature differences here. 1 part in 100,000. This is the tiny temperature differences. Like, we're not talking about 5 degrees here. These temperature differences are like 0.00001 degree up or the same amount down. This is such a tiny, tiny temperature difference. And yet the Planck satellite was able to find this with percent level precision on these tiny, tiny scales. And it was able to show us that we have these really hot spots and cold spots, which is exactly what we'd expected to see, but with incredible precision. So this is too basic, but I missed it. How are you measuring photon temperature? This is a great question. And also one that I always have problems answering because I'm not an experimentalist. Microkelvins, thank you. Thank you, David. Yes, microkelvins. So what you can do is you can send a satellite to space where you keep the spacecraft very, very, very cold with not much else interfering with it. Of course, you're going to have some background noise from galaxies, which is always a problem, from the Milky Way, which is a problem. You're going to have a lot of background sources. But what you can basically do is measure the amount of energy you get hitting your telescope. And you do a pixel decomposition, and at each point you measure the amount of energy you're getting, and you can use that to turn it backwards and understand the temperature of the photons. And I cannot go into too many more details because I always forget how experiments work. It's an experiment, it does cool things, but it's basically measuring the energy of the photons. I hope that answers your question at least to a good approximation. So why are these temperature differences important? What do they tell us? And they tell us a lot, actually. The answer to that question is a lot. Because by measuring these photons have not really done anything in the last 13,500 years since they've traveled towards us. They haven't really done much. They're not energetic enough to be absorbed or be emitted by other things. So they've basically traveled unhindered. Other than some, lensing effects or going into potential wells and coming out, they're largely unaffected. Which means by getting a map of the CMB photon temperature anisotropies, what we're actually getting is a snapshot of what the universe looked like 380,000 years after the Big Bang. So what this image shows us, the one on the right especially, it gives us a percent level precision measurement of what the universe looked like 13.5 billion years ago. Very nice question from Paul here. Does the left side of the angular CMB graph tell us that even if we had more precision, there would not be more variation texture at the small scales within these pixels? So let me answer that question in 2 minutes. I think I know where you're going with this question, but let me answer in a sec. So in fact, let me just skip to a specific image here. So what I'm showing you here is always the temperature anisotropies. And I just want to skip forward 2 slides, and I want you to focus on one specific thing, and then we'll go back. So if I skip one more, let's not get ahead of ourselves, and just focus on the top left one here. So ignore the other 3 and just focus on the top left that is labeled as temperature. Now what you can see here is actually when we turn this graph of the CMB into an actual data plot that we can use. So on the horizontal axis, you can see the scales in the night sky. So on the left means we take a 90-degree chunk of the night sky. On the right, it means we take like a fraction of a degree of a chunk on the night sky. You can see here that we have all of these red points, which correspond to the actual data from Planck, the latest data released from Planck, and the blue line, which is our best attempt to try to reproduce the data. And what you can see here is that the blue line very nicely agrees with the red dots. Now, these red dots do have some uncertainty associated to them. And this is these vertical lines that you can see on the red dots. Again, we're just focusing on the top left right now. In the top left, you'll see there are 2 panels. The top one where we have this nice wiggle shape, and then the bottom one, which is more or less straight. In the bottom one, it's what we call the residuals. And this just shows us how good our model compares, how accurately our model can reproduce the data. But just focusing in the top left panel here, the very top left one where we have these pretty wiggles, you'll see there are these vertical lines. These vertical lines are the error bars, our degree of belief in these data points. Now, what you'll notice is that as you go to the right-hand side, the error bars are very, very small. So on the left-hand side, they're a bit big, then in the middle, they're ridiculously small, and then they start getting big again right at the tail on the right-hand side. So what is happening here, and I really hope this is going to answer Paul's question, on the right-hand side, we are limited by the precision of the satellite. This is going to really, really, really small pixels in the sky, really, really tiny degrees in the sky. And here we are going to be limited by the fact that we need more precision. The more precision we have, the more this is going to shrink. On the left-hand side, however, on the very left-hand side where we have these big error bars, this is not limited by an experiment. This is limited by what we call cosmic variance. Now, cosmic variance is basically the problem that we only have one universe to do our studies in. And I say here that on the left-hand side, we're taking 90-degree chunks in the night sky. Now, if you divide the night sky into 90 degrees, you basically only have 4 maps of 90 degrees, which means you don't have a lot of statistics, and so your uncertainty is larger. If you move 1 point to the right, we're taking 60-degree chunks in the night sky. This is still something that you can only take 6 of, so your uncertainty is going to be larger. And this is something that you cannot fix with more experiments because we are still limited to the fact that we have one universe. So, Paul, back to your question. On the left-hand side here, the uncertainty comes from the fact that we only have one universe. On the right-hand side, which is where we head to lower and lower and lower scales, here we are limited by the precision of the satellite itself. So I just pressed the wrong button. Sorry, that meant to bring myself up. I hope that answers the question. So just to recap here, we have this prediction that we have these tiny, tiny temperature differences in the night sky. We have these tiny, 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 tiny temperature differences in the background light of the universe, this afterglow of the CMB, and this is something that we have now been able to measure. And I'm going to take some tea and give my brain a second to catch up. Using tea as a good pause. I'm still undecided about this tea. Okay, so we predicted this background afterglow of the Big Bang. We have measured it. We predicted these anisotropies. We have now measured them. Anisotropies just means these tiny, tiny temperature differences. And the reason this is cool is that this tells us really a lot of information about the CMB. This really tells us a lot of information about the universe. And I'm just going to before I walk you through and show you exactly what we can learn here, I want to take it back a step. Because I always talk about the CMB temperature. And this is really cool. This is one of the things we've been able to measure. But it is not the only thing, which you might already have gathered by the fact that we just had 4 panels and we were focusing on one. So when you get these photons from the CMB, you can measure their temperature, but you can also measure in which direction they're vibrating. So photons are just particles of light. So light behaves as both a particle and a wave. So every photon has a specific wave associated with it. And this wave can vibrate in different planes, in different directions. Which means when we get the photons from the CMB, we can measure their temperature, but we can also measure their polarization. So in which direction are these photons vibrating? And additionally, we can measure the lensing. So how much of these photons have been distorted by things between the CMB and us today. And this means that we actually get 3 maps from the CMB, not just the temperature one, which is the one I always show you, but the other one that we get is actually the polarization and the lensing maps. So what you can see here now are the 3 different maps we actually get from Planck 2018 data. Top left is temperature, top right is polarization, and bottom is lensing. Now within the polarization, I should mention that there are 2 different types of polarization that we could measure. One is what we call E mode and one is what we call B mode. And it basically just depends in which plane the photons are rotating. But today we're only going to focus on E mode for now at least. So these are the 3 maps we have from Planck: temperature, E mode, and lensing. And if you compare temperature and polarization, you can put them together and get what we call the cross-correlation of temperature and lensing. And each one of these maps independently give us a huge amount of information. So showing you the same figures again, as I showed before, now we can go in more detail. In the top left, we see the map of the temperature. In the top right, we have the polarization. In the bottom right, we have the lensing map. And in the bottom left, we have the connection, or how connected the temperature and the polarization map are. This is what we call the temperature polarization cross-correlation. And for each one of these, you can see we have a lot of data points. And for each one of these, we have the model in blue. Now, if you focus on the bottom right one, you'll see we don't have so many data points because reconstructing or getting the lensing data from the CMB is very, very difficult. But we can get temperature and we can get the polarization ones. So this already gives us a lot of information. And I want to walk us through a bit, like, what exactly is this telling us? So I'm just going to go through the slides here, and this is going to get slightly technical, but let me just skip this one a minute and go to this one here. So I want to focus on all of the different type of information we can obtain from this map here. Now, if anything gets technical here, please do ask me. I am using slides that I prepared for a talk at a conference with cosmologists, so I know that the images I'm using are a bit more technical than what I usually use in my streams, but they're also really cool. Okay, so first of all, by looking at this tail in the temperature and the cross-correlation maps, we can learn about inflation. Now, inflation was this hypothetical period in the early universe where the universe expanded exponentially. It went from being very, very small and very hot to being very, very big and very cold. This was inflation. And by looking at where these data points lie, where the arrows are pointing, we can learn about inflation. What else can we learn about in the CMB? Well, the position of these peaks, you see that we have these kind of oscillations, these mountains and these valleys. The position of these valleys tell us, this is what we call the acoustic oscillations, and this tells us about the amount of dark matter we have in the universe, the amount of dark energy we have in the universe, the age of the universe. It tells us about basically our standard model of cosmology is hidden within these peaks. And this is why we say that the CMB is the biggest piece of evidence we have for our current understanding of the universe. Our current best understanding, our best model of the universe is what we call lambda CDM. Now, within lambda CDM, what we have is a universe that is made 5% of normal matter. So everything you see, everything from me to my tea mug to the night sky that you see, all the stars, this is only normal matter. Normal matter only accounts for 5% of the universe. There's another 25%, which is in the form of dark matter. Now, dark matter is this weird type of matter that interacts via the gravitational force, but doesn't interact via the electromagnetic force, which means you cannot see dark matter. It does not emit light, it does not absorb light. As far as light is concerned, dark matter is not there. So dark matter should actually be called invisible matter. And then the remaining 70% is in the form of dark energy. Now, dark energy is this weird type of energy that is driving the accelerated expansion of the universe. And that's pretty much everything we know about dark energy. So lambda CDM is what we call our standard cosmological model. Lambda is for dark energy, CDM is for cold dark matter. And the thing is, if you change any of the components that we have here in this, so if you change the amount of dark matter, if you change the amount of dark energy, these peaks will move position. So by measuring the CMB, by getting the temperature, the polarization, the cross-correlation of the CMB, we can know how much dark matter there is in the universe, how much dark energy there is. Because else, if we changed any one of those numbers, this picture would not look the same. So the blue line that you see here, the data is what it is. These red dots is what we've observed. But if you change the amount of dark energy, this blue line is going to change. And the blue line is our prediction. Now, we want our prediction to match the data. And the only way to do that we've been able to find, the only way to get this blue line to go through all of the data points here is by having dark matter and dark energy in the universe. But we're not done. There's still a lot more we can learn here. So let's move on. In the tail, in the right-hand corner, the right-hand side of these maps where the arrows are pointing, we can understand how the very first elements in the universe were formed, how hydrogen was formed, how helium was formed, and how much hydrogen and helium were formed, how much lithium was formed. Light would be considered part of the 5%. Yes, light is part of this 5%. Light is normal matter. which is why all the light you see coming from stars, all of this is normal matter. Light is just a small fraction of the universe. It is a fraction of the 5%. But yes, light is a very, very small fraction of this 5%, actually. What else? What else? Let's see. So honestly, I have not looked at these slides, so we're just going through and seeing what's... I don't remember what else appears on the screen here, so we're going to figure this out. The places where the arrows are pointing now tell us about reionization. Now, this is the point in the universe where the first stars could turn on. Not the first stars directly, but where there was enough light in the universe to ionize everything again. So this is really when the first stars really began to emit enough light that this light could reionize, or just give a kick of energy to the hydrogen atoms in the universe. So by looking at these specific points that the arrows are pointing to on these maps, we can learn about when the universe became visible, filled with stars. What's up next? Let's see. Okay. What else we can learn here is dark matter, dark energy. We've covered those, but now we've moved slightly to the right. And neutrinos. Neutrinos are these tiny, tiny particles that are zipping through the universe. They don't really interact with much, but they can be dark matter. But they are also part of the 5% that we know of, and we can learn about them by using those bumps there. And finally, we have late time effects. So everything that's happened after the photons left the CMB on their way to us. This is what we get from the lensing map, and right from just at the left-hand side of the temperature and the cross-correlation map. So by looking at these 4 maps, we can get all of this information. And again, I just want to emphasize here, let me just do that, yes. I just want to emphasize here that these maps are independent. You don't need all 4 of them. You can take the temperature one and get information. You can take the polarization one and get information. You can take the lensing one and get information. And from all of them, we are recovering lambda CDM. The lensing one doesn't give us exactly lambda CDM, but close enough. There's a tiny, tiny anomaly there. But the temperature and the polarization maps are independent of each other. And they give us, all of them consistently give us this lambda CDM picture. This picture of a universe dominated by dark matter, by dark energy, and with a very, very small amount of normal matter. So in answer to the question of why is the C important, I hope I've just shown you everything the CMB can tell us, everything the CMB has told us. All of the data I was showing you here was from the Planck satellite. The mission, the space-based mission that gave us its last date in 2018, it started taking data in 2009. It started taking data in 2009. It released its first data in 2013, second data batch in 2015, and now the final date in 2018. So why should we care about the CMB? It is a prediction of our standard model of cosmology. It is a prediction that we have observed. And by measuring these tiny, tiny temperature differences and the polarization and the lensing of these photons, we can say that the universe is made up of normal matter, dark energy, dark matter. And I say 5%, 25, 70, but we actually know this even more precisely. We know that the universe is 26.5% dark matter and 4.9% normal matter and 68.9% dark energy. We know this with incredible precision, thanks to the data we have from Planck. So how could we not love the CMB? It has told us so much about the universe. It has also helped us understand how old the universe is, when the first stars began to turn on, and even what this early period of exponential expansion might have looked like. So the CMB has already told us a lot of information. I hope I've just convinced you of that, and we've seen how we get this information from the CMB. So by that alone, I don't know how anyone could possibly say that the CMB is boring. But the story does not end here, because there is still more that the CMB can give us. I should actually drink water as well. It's just guzzling my tea here. So why do I say that there is more the CMB can give us? The temperature maps, the temperature anisotropies we have measured with incredible precision. And this is what Planck was designed to measure. Now, it also measured polarization and slightly measured lensing. But the precision on the polarization data is substantially less because Planck was optimized for temperature. This is the first thing we wanted to measure. This means that there's still a lot we can do with polarization. We can still push that further than what we have. We can still go to smaller scales. We can still probe tiny, tiny, tiny patches of sky. So we can still get more polarization data, and we can still get more lensing data. And now I want to go into the polarization, because I mentioned before that there's two types of polarization. There's the E modes and the B modes. Now, the B modes were not measured by Planck. Planck could not measure B modes. So E mode and B mode is really just a difference of in which direction these photons are oscillating. So whether they're vibrating in a linear way or in a circular way. So we call it E mode and B mode, but it's really just about how these photons are oscillating or how they're vibrating. Now, the cool thing is we can predict a certain amount of polarization within lambda CDM, both of E mode and of B mode. But Planck itself could not measure the B modes because it was not designed to measure B modes. And why are B modes important, you might ask? Well, B modes can actually really push our understanding of this very, very, very first few seconds of the universe. Now, the B mode polarization could actually measure the background gravitational wave signal that could have been left by inflation itself. So if the universe went through a period of exponential expansion, which we believe it did, this would have been dramatic enough that it would have created ripples in the background of the universe, ripples in space-time. And these background radiation of gravitational waves could appear in the B mode polarization. So if you have inflation that produces gravitational waves, and we believe that every model of inflation should produce a certain amount of gravitational waves, this gravitational wave background could be imprinted on the B modes of the CMB. So if we were ever able to measure these B modes, we would be able to say if inflation happens how we think it happened. And if not, if we never find this background gravitational wave signal, we have to ask ourselves what's wrong, because inflation should produce this background signal. So getting a B mode experiment that would be able to measure this would be amazing. So the CMB has given us a lot, but there is still a lot more to do. And to show that, I'm going to bring up my slides again here. And I see that the chat has gone quiet, so I hope the chat is still, I hope the YouTube connection is still going through. If anything's happened to the YouTube connection, of course, you can't really let me know. But I'll just assume that everything is still working fine. And as always, is that if anything of what I'm saying is not clear, please do ask me questions. I know I'm rambling slightly. I know I might not be as coherent as usually today because I've had a few glasses of wine. But hopefully everything is clear and understandable. So what I'm showing you here is the future of CMB measurements. Now, what you can see in the top line here, the top one where you have these temperature, these kind of wiggles, the topmost line here is the temperature polarization. Sorry, the temperature anisotropies of the CMB. We are here. Thank you, David, for confirming. The second one you see in the middle is the E mode polarization, and the bottom one is the B mode polarization. The the dashed line you can see is our prediction from lambda CDM. And let's go through the different colors here. In blue, we have the Planck data, which you can see, especially in the top one, gives us a huge amount of precision. But now if you focus on, for example, the orange and the green, these are the Atacama Cosmology telescope and the South Pole telescope. And you can already see that the orange and green, especially in the temperature, have already pushed it a bit further. Atacama Cosmology telescope and South Pole telescope are ongoing ground-based missions that are pushing our measurements further. But they're not really interested in temperature, they're more interested in polarization. So if you focus on the middle panel here, the middle one, this is the E mode polarization. The dark blue is Planck. And if you look on the right-hand side, you'll see there's pink and light blue. Pink is the Atacama Cosmology telescope polarization data, and the light blue is the South Pole telescope polarization data. And you can already see that we've got kind of 25% further than what we did with Planck. We've been able to push it to even smaller scales. So we are really tracing these small bumps at the end. Again, these are missions that are still ongoing. They are still taking data. They are still pushing our understanding of the polarization. And then if you focus on the bottommost one, this is the CMB B modes. And you'll see that we have some measurements from an experiment called BICEP, shown in this kind of burgundy color. We have some from the two polarization missions from Atacama, and from the South Pole Telescope. In yellow, you can see ones from the Polar Bear mission, which is so good at naming things. Polar Bear is in Antarctica. We have a mission in Antarctica called Polar Bear. Of course we do. But you can see that none of these measurements of the B modes really reach the same type of precision we obtained with Planck for the temperature measurements. So what we would really, really, really like is to have a mission, an experiment that can measure the B modes of the CMB, because this would really help us understand the early universe, the first few seconds of the universe. And there are missions planned to do this. One mission is the Lightbird mission. Lightbird has been approved by the Japanese Space Agency. It is a Japanese-backed mission. The European Space Agency may still join. It is not completely clear. They may join, they may not. But in any case, it will fly regardless because Japan has already funded it. So the Japanese Space Agency, JAXA, has already funded the Lightbird mission. There are no bears in Antarctica, no, but there is a polar bear mission. I know. It's, yeah, physicists are bad at naming things. Now, Lightbird is a space-based mission that is designed to measure the B-mode polarization. It will also get some measurements of the E-mode polarization, but its main objective is to measure B-mode polarization. Now, this is amazing because if Lightbird doesn't measure what we expect, lambda CDM is wrong. If Lightbird doesn't measure any B modes, our understanding of inflation is wrong. If Lightbird measures something different to what we've predicted, we need to go back to the drawing board. So Lightbird is going to give us the B mode measurements, hopefully. And this is really cool. Now, Lightbird is, I can't remember the exact launch date, but I do believe it is 2027. In any case, it is within the next 10 years that Lightbird should launch, which is really cool. What blows me away just as much as the finding is the fact that we learn to measure variables. I was reading a question and it just jumped away. We learn to measure variables like light temperature, oscillating photons. It is really cool when you think about the type of measurement we're doing and the fact that we built these spacecraft, sent them up to space and got these measurements with percent level precision. And we use that to say, hey, look, I know what the universe did 13.5 billion years ago. It's amazing. I will never get over telling people how amazing the CMB is because it's amazing that we've been able to measure it. It's amazing how much information we've been able to get from it. And the fact that we've been able to put it all together and say, look, I think I've understood a lot of what's going on in the universe. It's really cool. You probably said this already. If the polarization is a direction for the light waves, why would the orientation be anything but random? Excellent question, Paul. Really, really excellent question. The reason is, let's go back to a cosmology lecture, and this is a very long, complicated question to answer. We'd really need to go through a whole cosmology course to answer that properly. But basically, the way the photons interact with other things in the medium means that they're not necessarily random. Now, for an example, if you have this background gravitational wave signal, this is going to slightly distort the way. Sorry, let me get this straight because we don't want to say something stupid here. Right, if you have this background gravitational waves, it will very, very slightly disrupt what we call the metric. I'm just thinking if what I'm saying is reasonable. You can imagine that a lot of these things in the universe, for an example, this background signal, will affect the overall fabric of space-time very, 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 very slightly, especially these background gravitational waves, which means the way the photons fall into these overdense and underdense regions is very slightly different. And this in turn affects the way the photons break away and the angle in which, or the direction in which they are propagating. I know that was a very hand-wavy explanation. I can assure you that if you do the math, it checks out. But it is quite difficult to really understand how this happens, especially as I honestly wasn't prepared for that question, Paul, and that is an excellent question. But if that explanation isn't satisfactory to you, I'll come back to it another day because that's the best I can do for now, I'm afraid. But basically, you would expect that the polarization is completely random, and if it is, then you don't have any B modes, for example. But if you actually do find this slightly preferred direction, it means that you have some type of thing that is causing this preferred direction, which would be the B mode signal in the background. I hope that helps. They are cleverly disguised as penguins. Yes, the polar bears are hiding as penguins. There is also a cosmology experiment called Pingu, and I believe Pingu and polar bear are very close by. We're very bad at naming things. Okay, so just to recap here, the CMB has already given us a lot of information, but there is still a lot more to do with polarization data. There is still a lot more to do with the lensing data, which I haven't really gone into. And these are things that we expect to get better measurements of within the next 10 to 15 years. Now, if the B mode measurements turn out to not support lambda CDM, then it means our model is wrong. Right? It could throw everything out. And I know that some people were disappointed because CMB found no changes to what we expected. Every time we get new data from Planck, we find that the universe is flat. We find that the universe obeys lambda CDM to the best of our knowledge from the CMB. We find that there are no non-Gaussianities, which would have been strange things happening in the early universe. Like all of the ways that we could find new physics within the CMB, we didn't. We just consistently found lambda CDM. When Planck released its latest data in 2018, there was a slightly provocative title in the press release, like Planck finds the most boring realization of the universe possible, because everything was confirmed. But your model being consistent and being confirmed is always good. It would be fun if things didn't work out, because then we have stuff to play with. But it's also fun if that doesn't happen. So if we ever get a B mode measurement, which we might do with Lightbird, it will help confirm or rule out lambda CDM. And it will also help us understand the first few seconds of the universe and everything that could have produced this background gravitational wave signal. And I am tying together gravitational waves and CMB here, which is two of my favorite things. Yeah, the experiment called Holy Cow is definitely on the contenders for the best experiments out there. So the CMB has allowed us to confirm that there is dark matter in the universe, that there is dark energy in the universe, that the universe is about 14 billion years old. The universe is, to the best of our knowledge, flat. The universe contains only 5% matter. We know when the first stars began to turn on. We have an approximate idea of what inflation looked like. And this is just from the temperature and the E mode polarization. But we can still push the E mode polarization further. We can still push the B mode polarization further. We can still push lensing further. And nowhere today did I talk about the other amazing thing in the CMB, which I'll do a whole stream about at some point, which are spectral distortions. So I mentioned that, in fact, let's go to the way I did this in my presentation, because I liked how I did it in my presentation, actually. Okay, so the CMB, this amazing map that we have from Planck. We have these tiny, tiny, tiny temperature distortions. We have these tiny deviations. And now I want to do something very, very horrible, and I want to smooth out these temperature differences, and I want to move beyond these tiny, tiny temperature differences. So let me just smooth them out in a very nice way, just like smoothed out the CMB. Just hated doing that, but needed to be done. Now, the reason I wanted to do this is because the CMB is an almost perfect black body. This means that it absorbs and emits light at every possible frequency. In fact, the CMB is the most perfect black body we have ever found. But it is not completely perfect, and therein lies another huge thing of the CMB. There could be tiny, tiny, tiny deviations from this perfect black body. So just tiny places where we don't emit and absorb every possible frequency. And these tiny differences from this perfect black body is what we call a spectral distortion. Now, spectral distortions are predicted to happen within the standard model of cosmology. If lambda CDM is correct, we should measure spectral distortions of 10 to the minus 8 in some specific units. If we do not measure spectral distortions of 10 to the minus 8, lambda CDM is wrong. There is no way around it. If we do not measure spectral distortions as predicted by lambda CDM, it's a prediction by a model that we do not measure. Lambda CDM is wrong. However, have we ever measured spectral distortions? Unfortunately, not yet. We have been able to say that if there are spectral distortions, they have to be smaller than 10 to the minus 5, which is great. And this was done with the FIRAS mission, which was joined with the COBE mission that launched in 1992, the first one to measure the anisotropies. The FIRAS mission was able to show us that the CMB is indeed a perfect black body, and if it has any changes from being a perfect black body, they are smaller than 10 to the minus 5, which is 0.00001, which is great. But lambda CDM predicts 10 to the minus 8, so we need to go beyond this. We need to go lower. If we don't measure what lambda CDM predicts, lambda CDM is wrong. But it's not just lambda CDM. If dark matter isn't as cold as we think it is, you'd get a different amount of spectral distortions. If you have primordial black holes, which are black holes formed in the early universe that are evaporating today via Hawking radiation, you produce spectral distortions. If you have matter falling into primordial black holes, you produce spectral distortions. If dark matter decays and it goes from being big to being small and just kind of decays and dies away, you produce spectral distortions. If we ever get a mission that could measure spectral distortions, not only will it be a key test of our standard model of cosmology, but it will tell us about all of these other models. And we don't yet have a mission to measure spectral distortions. The reason is people think the measurement is difficult. Of course, it's going to be difficult. There's a lot of galaxies in the way. There's a lot of light in the way. There's a lot of dust in the way. But 50 years ago, people didn't think we would measure the CMB temperature anisotropies, and we have. 30 years ago, people didn't think we would measure the precision we have with Planck. They didn't think we'd measure the lensing that we've measured with Planck, and yet we have. And currently, people don't think we'll manage a spectral distortions mission. I think we will someday. I'm very optimistic, and I've worked a lot on spectral distortions because to me, it's a topic that is amazing. It is an untapped resource within the CMB. It is just up there waiting for us to go up and measure it. And there is so much we could do with spectral distortion, so many things we could understand, so many things we could learn. And it's just there waiting for us. Every few years, a group of people get together and propose a spectral distortion mission, and it's never funded. It hasn't been funded yet. But I really, really hope that in the future, we will get a spectral distortion mission. Just going to show you one more plot here. So what you can see on the right-hand side is what we hope to do, what we could potentially do in the future. So you can see here, this dot dashed line is what we might do if we have a Pixie-like mission. So Pixie is a mission that was proposed. All of these things down here, these dark blue ones, I'm moving my cursor as if you can see it. You obviously can't see it. The dark blue and the green lines at the bottom are what we'd expect within lambda CDM, within our standard model. The light blue one, for example, is decaying dark matter. And you can see that it's already with something that we already have the technology to build. This Pixie mission is one that we could already build today. So the potential is there. The potential of discovery is there. It's just really just waiting for us to go and measure it. I'm just very quickly going through the slide, seeing if there's anything else I want to show you. There is not. Okay. So let me recap here. The CMB, the cosmic microwave background radiation, is this background light that we can see in any direction we look in the night sky. It is a prediction of our hot Big Bang cosmology. It is a prediction that we have observed. This background light is there. This background light is at an average temperature of 2.73 degree Kelvin, minus 270 Celsius, minus 440 Fahrenheit. But within this background light, there are tiny, tiny, tiny temperature differences and tiny, tiny, tiny differences in the polarization angle, the direction in which these photons are vibrating. We have been able to measure the temperature differences. We have been able to measure some of the polarization differences with a precision of percent level. which has allowed us this measurement of the CMB. Not only was it a prediction that we've measured, it has confirmed our standard model of cosmology. It has confirmed that there is dark matter in the universe, that there is dark energy in the universe, that the universe is almost 14 billion years old. It has confirmed that the universe is probably flat. It has told us when the first stars began to form. It has told us about this early inflationary period. But we're just scratching the surface of the CMB because we've exploited the temperature anisotropies. We're getting there with the E mode polarization. The B mode polarization is waiting for us. Lensing is there, still needs improvements. And spectral distortions are an untapped resource. They're just there waiting. So much discovery potential still just hiding in the CMB. I don't see, honestly, how anyone could say that the CMB is boring or that there is nothing left to do with the CMB, because there is so much left to do with the CMB. We are just getting there. We have understood the temperature anisotropies, but there is still so much more that can be done. There are still so many more CMB missions ongoing or planned in the future that will help push our understanding of so many things. I can't wait to see what we're going to do within the next 20 years with the CMB, because we've come so far in the last, like 20 years ago, we didn't even have the first measurement. Okay, we had the first measurement from COVID. We didn't have the measurement from WMAP. We were just starting to get there. Like 25 years ago, we were just starting to push our understanding of the temperature anisotropies. And we've come so far in 25 years. And I think in the next 20 years, we're going to have another big step forward in our understanding of the CMB, either with a spectral distortion mission or with B modes. But there was so much left to get from the CMB. There's so much more that it can tell us. So let me go back to the comments here, because I know there were just 2 comments that I didn't see there. We need some good marketing slogans for new missions. Don't let the CMB pass you by. Yeah, I can assure you we keep trying, especially with the spectral distortion mission. I've been involved in 2, 3 by now, a couple. Yeah. They don't get through, but there is hope. I do believe, I am optimistic, I do believe that within the next 20 years, we will get a spectral distortion mission funded. I really do think we will. I need a high-level understanding of all missions pending and processed to determine which are advanced. Ooh, asking for a lot here, James. So, briefly, this is not going to be a high-level understanding, but briefly, Atacama Cosmology Telescope is ongoing, taking temperature data. It also has its polarization counterpart that is taking E-mode polarization. This is a ground-based mission in Atacama Desert. South Pole Telescope and its companion South Pole Telescope polarization data is ongoing, taking data of both temperature and polarization. The Polar Bear mission is a ground-based mission that is taking data of the CMB B-mode polarization. Lightbird is a planned mission in the future that is going to take data of the B-mode polarization space-based mission. Also, not mentioned today, CMB Stage 4 is the next big step in a ground-based mission for CMB. CMB Stage 4 is something that is going to be a thing within the next few years. It will measure temperature and polarization of the CMB from the ground. The advantage of doing it from the ground is you can stare more intently at a specific region, so you can get more precision on a specific region, but you don't get the whole night sky coverage. So you get small coverage, but you can stare deeper with that coverage. Simon's Observatory is a ground-based mission that is also set to measure temperature and polarization, and, I believe, lensing, also set to go ahead within the next 10 years, also ground-based. And what am I missing? Then there are the ideas that one day, maybe, we will get, I think I mentioned Lightbird already. Lightbird is the planned mission to measure B modes. It's a space-based mission approved by the Japanese Space Agency. I think I mentioned Lightbird twice. And then maybe someday we will get a spectral distortion mission. We proposed the core mission, which would have been a spectral distortion mission. Core was never funded. Pixie was also a proposed spectral distortion mission, not funded. PRISM is a potential spectral distortion mission, still waiting to hear back. Voyage 2050 is the next step. 2050, like quite a few years away, of where we might want to go in 25 years. There is mention in Voyage 2050 of a spectral distortion mission, but that's a long way away. So off the top of my head, those are the key missions. I'm not sure if that counts as a high-level understanding. That was a very quick summary. That's what I can do off the top of my head, and I probably forgot a mission there. Apologies to the mission I forgot. I hope I went through the main ones. I went through at least the ones that I'm aware of or involved in or that I have worked on at some point or that I'm hyped up about at least. So there's still a lot of CMB activity ongoing. There's still a lot to do with the CMB. So I hope I'm losing my voice. This is not like a COVID or flu cough. This is just every spring I get this cough. So do not worry about me coughing. It is nothing serious. I just get it every spring. So I hope I've convinced you somewhat today that the CMB is one of the most incredible things we have in the universe. The CMB has told us a lot, but there is still so much more that the CMB has to offer. We've just began to see the tip of the iceberg with CMB data. There is so much more to do. There's so much more to learn from the CMB. And I really think within the next 25 years, we will push our understanding of the CMB and of the universe even further. And I, for one, cannot wait. Okay, I hope I convinced you that the CMB is awesome. Just in case you'd forgotten how much I love the CMB, you know, heard me praise the CMB for a whole hour because the CMB is amazing. Next week, we're going to cover holography. I know this was requested recently, so I will be joined by a guest from my office, not from my specific office, but from my building, someone from my group who works on holography. Now, we're going to talk about if that is in any way related to black holes, what holography means, how it relates to the holographic principle. So if you've ever heard of holography and have questions, now's your time. Next Sunday will be your time to ask. If you've never heard of holography, next Sunday is your chance to learn about it. We should be online next Sunday, same time as always, at 7 p.m. Central European Summer Time, which should be 1 p.m. East Coast Time, 10 a.m. West Coast Time every Sunday. Should be online next week, unless there's a last-minute change of schedule, still to be 100% confirmed, but we should be doing holography next week, next Sunday. I hope to see you all next week on Sunday. In the meantime, if you haven't done so already, please click the like button here below on the YouTube channel. This is how we push the engagement. Leave a comment if you want. Subscribe to the channel if you haven't already. I'm almost at 100 subscribers, and then I get cool things like customizing my URL. So please do subscribe to the YouTube channel if you haven't done already. And I will put some links to other videos that you might be interested in. I still need to figure out how to make panels appear on my streams. That's going to happen. So please do subscribe. If anyone wants to reach out to me, you can find me on Twitter, DCHooper91 on Twitter. Some of you are watching on Twitter, I know as well. Or you can always contact me using Cup of Cosmology email address, which is contact@cupofcosmology.com. And as Paul is saying, please do share this out to your friends, your followers, your family, to people you don't like. Just send this around, you know, shout it from the rooftops, because why not? Everyone needs more cosmology in their lives, at least I do. So thank you everyone for joining. This has been great fun. Thanks to all the regulars for popping in, and hello to everybody new. I hope you do all come back. I hope to see you all again next Sunday. And in the meantime, I hope you all stay safe